how viable is a big numerical reverse database to identify closed forms for real numbers, such as Simon Plouffe's inverter? Okay, this is kind of an interesting one, maybe. Okay, you've got the number 1.2736846. What is it? Where did it come from? You could just write it down, but it could be that that number is actually pi squared over 7. It could be that that number has a short sort of symbolic description. That number might be the square root of 2. We can write it very easily. Or that number might be something which we could describe as 1.41486342445, et cetera, et cetera, et cetera. It's a number that just seems like a random number. So some numbers, a very small fraction of all numbers can be described easily. So for example, rational numbers like 2/3, 0.6666666 recurring, that's a definite thing. If we just change one of those sixes out at the billionth digit, that wouldn't no longer be 2/3, and we might have no particularly simple way to describe. If we just change one digit, there's a pretty easy way to do it by just adding 1 over blah, 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 but 1 over 10 to the blah, blah, blah. But if we monkeyed around with a bunch of digits out there, there might be no simple description of that number. So the question is, which numbers have simple descriptions? First thing to realize is the fraction of numbers that are rational numbers. Okay, so we have whole numbers and we have rational numbers, which are ratios of whole numbers. So, 3/4, 7/8, et cetera, et cetera, et cetera. A little bit of a trickiness with rational numbers already that, 4/6, which seems like it's a definite number, is actually the same as the number 2/3. That's that we can cancel the extra factor of 2. And so what we might think of, you write down a number, any two numbers written down differently will be different numbers, but it isn't true for rational numbers. Even though those two numbers are written down differently, 4/6 and 2/3, they're actually the same number. They're equal. They're numerically equal numbers. And by the way, there's an even bigger trickiness, which is if we write down numbers as decimals, the number 0.9999999, 9's all the way down. Is that number the same as the number 1.00000 or not? Those numbers can be arbitrarily small different. Are they in fact the same number? For most purposes of mathematics, those are the same number, even though their representation is different. And that causes all kinds of difficulty in understanding how real numbers which aren't just whole numbers, work. So the question is, I was going to say, if you ask the question, is every possible number a rational number? The answer is no. When you have sufficiently many digits, any rational number is a ratio of two integers, and if the integer has, it's kind of a limiting thing. If we say there are an infinite number of digits, we can't get to the infinite number of digits with integers. It just doesn't work that way. There's more real numbers than there are integers. If you call the number of integers, it has a name. It's called Aleph 0. It's a so-called transfinite cardinal. Is the number of integers. Now that number I can't give you that number of M&Ms or something. That number is just a theoretical number. It's really an infinite number, but it's a particular kind of infinite number, Aleph 0. It turns out that the number of real numbers is basically 2 to the Aleph 0. Basically, you're for every there's a higher level of infinity that you get to that corresponds to the real numbers. So in a sense, that means there are many more real numbers than there are rational numbers. So the question is, if you have a number that comes out of a calculation and you say, I wonder whether, and that number you got by some numerical computation method, and you say, I wonder, I've generated 50 digits of this number. I wonder whether actually that number is pi squared over 7, whether actually that number is something that can be represented in a simple symbolic way, where if I had been smarter about doing the calculation and had done it kind of algebraically rather than numerically, I would have just got the answer pi squared over 7. I wouldn't have got this big block of numbers. Okay, so the question is there a systematic way to say what's the number that, given a series of digits, is it even close to a nice to describe number? Okay, the tricky part of this is there's this complicated trade-off. What's a nice to describe number? If this number was equal to let's say 2 over square root of 3, that's like, okay, that's fairly nice. But it's also really close to pi to the 17 over 742 minus the zeta function of 5 plus whatever. You say, well, that's not quite so nice. And you say, I'd really prefer to get the 2 over square root of 3 form, even if that might be a little bit further away from the actual digits that I have, or might not agree for as many digits or something. But so there's this question of, can you assess what is the likely nice number that might have been the nice to describe number that might be close to this real number that you have. Now in Wolfram Alpha, for example, if you just type in some random number, it will try and tell you nice possible closed forms. Closed form meaning something where you can just say the whole thing. You can just say it's pi. You're not saying it's 3.14159 ... and you don't say the whole thing. A closed form is something where you just say there's sort of the symbolic representation of it as it's square root of 2. It's, pi to the power e or something. Now, how does one do that? Well, there is a trade-off. How exotic do the formulas get? How many terms do the formulas have? And then what kinds of things appear in the formulas? I mentioned 2. Okay, that's pretty communal garden. I mentioned pi. Okay, that's a little bit more exotic. I mentioned e. That's probably a little bit even more exotic. Let's say I mention the golden ratio. Let's say I mention the Catalan's constant. I could start giving you all these named things which have occurred in the history of mathematics, but they get more and more obscure. And so the question is, if I've got a trade-off, if I say, well, this thing is really close to Catalan's constant cubed over 6, it's also roughly square root of 3, which would you pick? Well, or actually worse, it's equal to Catalan's constant over 2, or it's this combination of 8 square roots. Which do you pick? You kind of have to have this measure of what is the sort of lowest information content thing. In other words, if Catalan's constant requires you to know all this extra stuff from the history of mathematics to know about it, that's kind of a higher cost than if it's a few more square roots. So actually in Wolfram Alpha, what we did is, when we're trying to assess the relative importance or relative sort of complexity of these different kinds of constants, let's say, we just searched the mathematical literature and we said the more frequently the thing occurs, the less obscure it is, and the lower the kind of cost of producing it in a formula is. But there will be cases where there's a very, very obscure constant, but you might really nail this result by using that obscure constant, but you could also get a good approximation by using a slightly more complicated formula with ordinary constants. So basically that's the idea, that you have to kind of have this way of weighting these different pieces that you could put into your formula and say which ones are more important than which other ones. From a technical point of view, I mean, we've done a pretty good job, I think, with the one of these in Wolfram Alpha. The difficulty is more of a philosophical difficulty of kind of how do you represent each one of these things. That's the such and such constant is essentially a packaging of certain ideas in mathematics, where you say, and the result is such and such a function or such and such a thing, and you give that function a name. That's saying this thing, wherever it came from, we now know it as this particular name, and we can refer to it in that way. And it's a question of sort of what did you package in mathematics to provide in this form.